Okay, thanks, Lillian. Right, so I am Christene Lynch. I'm a postdoc at Curtin, and I will be talking about some work I've been doing to better the sky models used by the MWA EOR group to try to detect the EOR signal. So it's well known in the EOR community that the accuracy and completeness of the sky model used to do both the data calibration and the source subtraction is very important in our ability to make a successful detection of the EOR signal. This is really illustrated very nicely in this paper by Patel et al. 2016. So they simulate LOFAR data using 25 discrete sources. And they use these discrete sources to calibrate the simulated data and do the source subtraction. And this plot here on the left is showing the results from this analysis, where they show the 1D angular power spectrum for the residuals from the simulated subtracted data compared to the thermal noise that's expected for this data set, as well as the amount of power that's expected in the diffuse foreground. And there are two key effects to note here in this figure. First, on long baselines or small angular scales, there's an excess in the power in the residuals. This is due to, as they kind of argue through the paper, that this is due to an imperfect subtraction of these discrete sources in the foreground. They also note that there is a reduction in power on small baselines or large angular scales, and this is due to the fact that they don't include this diffuse foreground in their calibration. And so both of these effects can be explained by an incomplete sky model or an inaccurate sky model, really emphasizing the importance of getting this model correct. So recently the MWA has gone through an upgrade and has two new configurations. The one that I'm interested in is this extended configuration. So on the left is showing the footprint of the tiles for the new extended array. The green tiles are the new ones and the purple tiles are from phase 1. And what's most important about the extended array is now we have a longer maximum baseline. It's about twice the length as in phase 1. So we get better angular resolution, higher angular resolution imaging, allowing for better modeling of some of the foreground sources. In addition to this, though, because the new extended array doesn't include the core of the phase 1 MWA, the PSF for the new extended array is much better than for MWA phase 1. And so this plot here is showing the comparison of the PSFs. I guess to note, the ones you want to note in this plot are the top 2 lines for the extended array and then the bottom 2 lines in the legend for the phase 1. And you can see for phase 1, there is this rippling due to the side lobes in the PSF. And in the MWA phase 1 images, you can definitely see these ripples around bright sources, and this increases the noise in your images and reducing the sensitivity you can actually achieve. You can see for the extended array, the rippling has been suppressed, and so you get much better images and greater sensitivity in the extended configuration. So taking advantage of this new configuration of the MWA, I'm conducting the long baseline Epoch of Reionisation survey, LoBES. And so this uses the extended configuration of the MWA to observe not only the 2 main fields used by the MWA EOR project, EOR1 and EOR0, highlighted in the red circles, but also their neighboring fields. And this is because it's important not only to have accurate models of these sources in the primary fields we're using for the experiment, but also the sources in the side lobes of the observations of the field. And the survey is taken over a wide range of frequencies so that we get very accurate spectral modeling for each of the foreground sources. What I'm presenting here today is just images and data from this EOR0 and the neighboring fields. So I just wanted to give you a very general, broad idea of how I've gone about creating this catalog. There's a lot of information and steps that are not included in this, but this should give you a better idea of what I'm talking about later. So first, I created a deep wideband image. So this is basically just stacking across the full frequency range of lobes into a single image, convolving to the lowest angular resolution. So this achieves the highest sensitivity for the survey. So you can detect faint point sources, but also detect a lot of faint extended emission around these complex sources in the field. So I do a source finding on this deep image and then do what's called a prioritized fit on each of the spectral images. So in this prioritized fit, the source positions and source sizes are held constant while the flux is allowed to vary. And so this allows you to measure the integrated flux density for each of the Gaussians that are in your source models. And then take those flux densities measured in each of the spectral images and create spectral energy distributions, which are shown here. So this is the log of the flux density as a function of the log of the frequency. And what's included in the final catalog that we will use to calibrate and source subtract for the MWA UR project is the spectral information contained in these spectral energy distributions, as well as the source positions and the sizes of the source Gaussians. This is the deep, well, it's the -27-degree declination strip of the deep image. It's not the full lobe survey, it's just that one strip. Just, it's easier to display this way. And you can see there's like many thousands, tens of thousands of sources in this image. This is a 5 by 5 degree inset, and it's centered on one of these complex extended sources in the field. You can kind of get a sense of the image quality. There's not a lot of image artifacts around any of these sources, so it's very clean images. So we can compare the deep image to the deep image in Gleam to try to get a sense of what's been improved or what are we adding with the now extended array. So in the full deep catalog for lobes, there are roughly 81,000 sources. And in Gleam, in that same area on the sky, there's roughly 66,000 sources. So you're increasing the number of sources by about 15,000 sources in the lobes catalog. And you can see that the resolution is better because of the extended baselines, and you're getting much deeper, better sensitivity in the images. Again, because you're reducing the PSS better, you're reducing the sky noise. On the left, I'm showing the histogram of the flux densities for all of the sources in this deep catalog from lobes, where I've separated the single Gaussian sources from the multiple Gaussian sources. And this is really to highlight which sources are where in the flux density, kind of in the distribution of flux density. So what you see is that even though these multiple Gaussian sources only make up 5% of the total catalog, they are the brightest sources in these fields, and are very important to accurately model, because if you leave them in the field, they will leave all of this residual power. These are just some quick quality metrics of the catalog. So on the left, I'm showing a comparison of a predicted flux density for a set of bright single isolated sources at 151 megahertz that have been predicted basically by doing a cross match with a set of catalogs at different frequencies, and then using that spectral information to model and predict what the flux density of these sources should be at 151 megahertz, and comparing that to what it is in lobes. And you can see that the ratio of these two is centered around 1. There is a bit of spread, but it's acceptable for the work that we need to do with this catalog. On the right is showing the astrometry of the wideband image. So this is the catalog that I'm using to do this prioritized fitting. So it's very important to make sure that the positions are correct. And you can see that the distribution of the source offsets and declination and right ascension are very small. The average is about a half an arc second, and this is much less than the errors in the positional measurements. So we're okay with this offset. And then finally, I'm just showing some of the improved source peeling. So this is for 2 different sources in the EOR 0 field. And for both of these sources, on the left, I'm showing an image of the Gleam data that I'm using to test this source peeling, overlaid with what is currently in our MWA EOR source catalog. So for this source, it's a single Gaussian. And for this source on the right is 2-point sources. And then to compare that to what's in LoBES, I've shown the LoBES image overlaid with the LoBES model. So you can see it's much more complicated in LoBES. And then the bottom images are the residuals from peeling these two models. And you can see that the LoBES model peels more emission, and you get a better RMS in your residual images for the LoBES models. So you can see, though, that there is still some bright residuals even for LoBES. And so there's a few sources like these that need a little bit more hand-holding, which I'm currently trying to finish off and round off to complete the catalog. So I'm just going to leave you with my summary, and thank you all for your attention.